Hi everyone, my name is Vikrant Goyal and I'm here with my colleague Balaji. I'm an engineering manager at the data infrastructure team at Robinhood, and we are here to talk about our data lake. How did we move our data lake ingestion from 24 hours to less than 15 minutes? So this is the agenda. We'll follow the talk in 3 sections. First, we'll talk about the original data lake and the original ingestion framework that we started with. Next, we'll walk you through the design choices we made and the lessons we learned while using change data capture paradigms. And then Balaji will deep dive into how it all ties up with Apache Hudi to form the near real-time Lakehouse. So this is a 1,000 feet overview of how all the data moves at Robinhood, or a lot of data moves at Robinhood. We have several online databases, relational databases that support brokerage systems. Then we capture real-time events from our mobile and web app. And we also ingest a bunch of third-party data. Now, our infrastructure, systems provide these raw data from our warehouse to our data scientists, data analysts, data engineers, and then they use distributed computer systems like Spark to create more derived data sets that are further used for analysis, reporting, making data-driven decisions. So this is what we started with. Once a day, we used to do a full table scan of RDS databases. RDS, essentially, the AWS's way of RDBMS. So as you can imagine, there are some issues with it. Even when there are only small fraction of changes, we are basically snapshotting the whole table. So we had very high read-write amplification. We need to maintain very high I/O dedicated read replicas to run these large queries and isolate them so that they don't affect the primary. And because it requires so much read amplification, it was relatively slow, and we couldn't do that more than once or twice a day. So we had to live with 24-hour latency. And you can imagine, 24-hour latency is too much for a lot of business-critical applications. There are many use cases which require intraday information. So a common design pattern to solve these kind of problems is called CDC, change data capture. And in this, each CRUD operation that happens for the database is replicated from DB to a subscriber. And then the subscriber can in turn apply them to whatever sync they want. This is quite efficient / cheap and fast because you're only working with the deltas, only the changes. So next, we'll deep dive into how we do CDC using Debezium. Debezium is an open source Kafka Connect service. It's a distributed tool. It supports CDC from many relational databases like Postgres, MySQL, MongoDB, etc. We've been using it for more than a couple years now, and overall we have generally been quite happy with it, along with there are some learnings that we did on the way. So let's take a Postgres database as an example and zoom into it. So this is the high-level architecture. We have the primary RDS database who's taking the writes. Then Debezium captures changes from these primary RDS database and writes all of them to Kafka topics. On the consumer side, we have Apache Hudi running, which takes these incremental changes and writes them to our data lake in Amazon S3. It also updates the Hive metadata schemas along with it. Now, this is for incremental ingestion. For any incremental ingestion, you need an initial snapshot to begin with, on top of which you can apply these incremental updates. Now, Debezium does offer an out-of-the-box snapshotting utility, but in our it wasn't the best for us, and we'll talk about it why shortly. But basically, what we did is we built a custom bootstrapping mechanism. So we use the replica RDS for it. What we do is basically we created a utility called bootstrapping utility to Hudi's utility called Delta Streamer. What it does is basically runs a distributed read job on the replica RDS using Spark, creates an initial snapshot, on top of which we can apply the incremental ingestion. All right, so let's zoom into Debezium and see how Debezium itself works. First, we're going to take Postgres here as an example. First, for whatever database you're working with, you have to enable logical replication on it. Or in MySQL, it's called something else. But basically what happens is once you enable this, any updates or changes that are happening to the database, they'll be written to binary files called wall logs, write-head logs in case of Postgres. Second, Debezium can consume these vol logs using logical replication. It validates that the schema of these logs match what it has in Avro schema registry. We use Kafka schema registry in this particular case. And then it serializes all those vol logs into Avro and writes them to table-specific Kafka topics, which consumers can then read. So next, we'll talk about why did we choose Debezium over alternatives. Like Robinhood is an AWS shop, so the biggest alternative we had was DMS. These are the 5 criteria we had while we were evaluating Debezium. Number 1 was operational overhead. Debezium has high operational overhead. Like you have to maintain it yourself. You have to spin up your own Kafka Connect clusters, deploy it. You have to automate all the deployments, the configuration, everything. So yes, the operational overhead is high. As compared to that, like DMS just works out of the box. The configs are fairly automatable. So yeah, pretty good there. Talking about cost, like technically Debezium is free, it's open source, but you do have a lot of engineering cost to maintain all of that. On the DMS side, the engineering cost is negligible, but it is relatively expensive. Now here comes the positives for Debezium. Talking about speed, like it's super duper high as compared to DMS. Like in our benchmarking, which was done more than a year ago, by the way, but Debezium was more than 10 times faster than DMS. Talking about customizations, Debezium being an open source tool, like you can do whatever you want in it. Like we in fact have a lot of custom transformers we wrote for like very complex data types. On DMS end, we don't have that capability. And then for community support, Debezium has a very active and helpful Gitter community, while for DMS, you're limited to AWS support. So next, as I mentioned, we've been using this for a while. I'll talk about 5 major lessons we learned, if they're useful for you as well. Number 1 is Postgres primary dependency. Any kind of logical replication you want to do, it can be done only from the primary. It raises some risks because now you're playing with primary. If something happens to the primary, basically your service goes down, right? So there are 2 main risks around it. First, about disk space. If the Debezium consumer, it doesn't need to be Debezium, any logical consumer dies, like database will keep accumulating those vol logs and eventually it'll run out of space and your service will go down. So you don't want that to happen. So you have to build proper monitoring and alerting to make sure that it catches before that even happens. And secondly, each logical replication on a Postgres database in this particular case has some small amount of CPU. Like not a lot, it's 2-3%, but it can add up. So starting Postgres 10, Postgres comes inbuilt with a plugin called PG output. So that using that plugin, you can natively take out logical replication updates from the database. But if you're using an older Postgres version, then you have to install a third-party plugin, for example, Vault2JSON, to get those updates out. Those are relatively more heavyweight. So in our experience, like upgrading to Postgres 10 Plus was pretty much a prereq for this. Next lesson I'll sort of go back to was the initial table snapshot I talked about. So if you remember, I mentioned like Debezium does provide an out-of-the-box snapshotting mechanism, but we chose to go against it. The reason was the way Debezium does the initial snapshot is literally you tell it, okay, from this database, go and initial snapshot this table. It'll go, capture changes row by row, write them row by row to a Kafka topic or whatever sync you have. So for large tables, it's first of all slow. Secondly, it puts unnecessary pressure on your Kafka infrastructure and your, the primary it's reading from. The solution we built, as I mentioned, was using Spark and Hoodie. We created a custom tool that runs distributed queries on the replica and writes data to your sync. The third was like what data format to use. Debezium supports Avro and JSON. So we did these 3 benchmarking. So Avro, just JSON, and JSON with schema in the messages itself. About throughput for Avro, like we were able to get 40,000 messages per connector. I'll come with the per connector part after this. But yeah, 40,000 messages messages per second per connector. For JSON, we were only able to get 11,000, while for JSON plus schema, 3,000. And main reason for this was just the size of the message. Talking about data types, like Avro pretty much supports every data type you can think of natively, like most common data types you can think of. For JSON, it has a very limited number of data types it supports. And then talking about schema registry, Avro does need a schema registry that both the producer and the consumer will need to use. JSON and JSON schema, like consumers can infer the schema from the messages themselves. Next is how do we create multiple logical replication streams for horizontal scaling. So it's possible that you may, like I know I mentioned 40,000 messages per second from a single connector, but if you have a large service which has large tables, which gets like very bursty data, for example, you have an archival job which deletes data or like some kind of big batch job, those 40,000 messages per second can still end up being a lot. So what you can do is horizontally scale this. Divide your tables among multiple connectors on a database. So each, in our practice, we found that each connector that you set on Debezium on a single database can get around 40,000 messages per second. So you can horizontally scale this. One thing you have to be careful about is, I mentioned that every connector does require some CPU. So you can't just create infinite number of connectors. You have to be slightly wary about that. And last but not the least, everyone's favorite topic, schema evolution. So when we started working on this, we made an assumption the schema changes will be infrequent and mostly backwards compatible. It was a failed assumption, like definitely did not happen in practice. Some examples of non-backwards compatible changes were, the biggest one we saw was adding non-nullable columns. Like, often people don't realize that non-nullable columns are actually not backwards compatible, like, but yeah, that's the fact. So 99% of the times we saw this being an issue. Other types of non-backwards compatible changes are deleting columns, changing data types, and this can happen any time of the day. So being an infra team, like you end up being always on call, and that's not where you want to be. So the way we handle that is by freezing the schema. So whenever we get, our systems get a request that, hey, this is the database, this is the data set we want to onboard, we freeze the schema. Okay, these are the columns that we'll ingest to begin with. We freeze the essentially config of Debezium. To tell Debezium, these are the only columns we want you to replicate. Now, if any additions or any such things happen, like we don't make those changes immediately. We bash them for a later maintenance window. That maintenance window, like we basically have periodic jobs that run, go and checks all the data sets that we have to ensure that their schemas haven't changed. And if they have, we update our configs. The good thing about that is you're not always on call, so that's great. The bad thing about it is, yeah, your schema is temporarily out of sync. So yeah, that was all for CDC and Debezium. Next, I'll hand it over to Balaji, who can deep dive into how it all ties up with Hoodie to form a near real-time Lakehouse at Robinhood. Thank you.
Okay. Thanks a lot, everyone. Let's look at how we built our Lakehouse using Apache Hoodie. Okay, first of all, what is a Lakehouse? A Lakehouse combines the features of both data warehouse and data lake. Some of the core requirements that you need for building a Lakehouse are, like it has to support storing high quality data reliably with ACID transaction support. It has to be highly scalable and allow for decoupled storage and compute elasticity to basically support various use cases in data lake. And it has to be built using open data format because you don't want to end up locking into one particular vendor. And a Lakehouse must be providing direct access to files for supporting various applications like machine learning and other related applications. And to support quick and efficient processing, incremental streaming pipelines need to be built on top of data Lakehouse. And there are various use cases for a Lakehouse. For example, it can be used to build, it can be used to store raw data that's replicated from a different online stores and also any other sources. And also, you would want to store analytics and derived data that are built out of these raw data. And a data Lakehouse needs to be optimized for supporting all these use cases. So at Robinhood, we use Apache Hoodie as the Lakehouse platform. We store the raw data in Hoodie, and we are working on migrating our derived data into this platform. Let's look at Hoodie in more detail in a few slides. So what is Hoodie? Hoodie provides transactional support for data lake tables. It supports multiple processing engines like Spark, Flink, Presto, Hive, and so on, and allows for decoupled storage and compute architecture. You can think of it as a complete platform for performing streaming, ingest, and ETL, and provides native support for updates and deletes. And also, the streaming pipelines can be built on top of batch dataset using Apache Hoodie. There are two different storage modes in Hoodie, which we'll describe more in the later slides. Okay, so diving more into the features, the basic primitives that you need to build an efficient and fast data platform is support for upserts and incrementals. Like inserts, updates and deletes are basic operations that needs to be supported as first-class citizen. For applications like GDPR, CDC ingestion are like core to a data lakehouse management, and updates and deletes are essential part of that. And apart from providing a basic view of the data set, Hoodie comes with supporting what is it called, an incremental view of the table. Now, what does it mean by incremental view? So in a RDBMS database, we have what is called write-ahead logs that basically captures all the change logs that are happening on the database, all row changes and everything. And one can actually access these wall logs and stream the data out of it and build efficient replication out of that. In the same way, Hoodie provides query processing capabilities to incrementally read the changes that are happening onto the Lakehouse tables. And this can be done in an efficient way because Hoodie keeps track of incremental changes in its internal metadata, and from which you can basically build very efficient stream processing pipelines out of batch data set. So apart from all these primitives, Hoodie comes with connectors and platform features for performing streaming ingest. It provides automatic scheduling and execution of compaction to make the storage layout really optimized for queries. And it also comes with Z ordering and Hilbert curve and other kinds of data skipping indexes that you can build on top of Hoodie so that your storage layout can basically dynamically change depending on the query patterns that are getting seen. And apart from this, there are other pluggable features like indexing and other things that makes it a holistic platform for managing your lakehouse. Now, let's look at some of the basic basic features of Hoodie and how it is built. And we look at the storage layout first. So in order to provide isolation between readers and writer, Hoodie implements what is called multi-version concurrency control. So that basically means there are multiple versions of files lying around in the data set. And each version of this file is what is called file slice, is an internal terminology. And the collection of all these file versions for a logical file is called a file group. And for every single transaction, Hoodie is going to basically generate a lot of metadata around these file slices that are getting changed and other metadata that it wants to build other indexes. And it basically logs them into an timeline event log. At the same time, it also snapshots this data into an internal table. It's called metadata table, which is again built using the same Hoodie primitives. And at query time, Hoodie query support is going to interact with these metadata table to figure out the right set of file slices to be read to provide an efficient and quick serving of data. And this is the basic storage layout of a Hoodie. We look at two different storage formats that Hoodie supports and what are the pros and cons of them as well. The first is the copy on write storage type. I'm going to describe with some illustration here. So we can imagine that there are 5 records, A to E, 5 records are there, and which needs to be inserted into the data set. We'll start with an empty data set now. And Hoodie is going to start at being a transaction. Let's say the transaction number is 0. And it's going to, in this scenario, it so happens that it's going to create 3 files. And it's going to place the records based on whatever you see in the slide. And once the transaction is committed automatically, the future queries are going to see the changes of these data. A snapshot query gives you the latest snapshot of the data table. And so in this case, there are only 5 records, so it's going to return the 5 records. An incremental query for this commit is going to return only the records that are brought in by commit 0. And in this case, the same as what the table contents are, so you're going to see the same set of records. Now, the interesting part happens where there are updates. Some of these records are getting updated. And again, like this happens at, like, say, transaction time 1. And what Hoodie does is, Hoodie is going to first efficiently figure out what are the files, a subset of files, where this incoming records are present, the previous version of it is present. And it's going to read them. It's going to merge them with this incoming data set and write brand new versions of these files. And again, once this data is committed, the snapshot view is going to read the latest version of these Parquet files and going to give you the latest state of the table as of the transaction time 1. So incremental view for this particular commit is going to only return the records, the updated records that was brought in by this commit, which is 2 of these records. Now, just like in a similar example, you have like 2 updates. There's a second batch of records where there are more updates and inserts. And Hoodie is going to do the same thing. For updated records, it's going to read the previous version of the Parquet files, and it's going to merge with the incoming records, and they're going to create the brand new version of the files. For inserts, there are multiple modes. There is one mode where it basically optimizes for file sizing. So what that basically means is there is an record placement algorithm within Hoodie, which keeps track of different stats and figures out what is the right file which can be expanded. And what that provides you is a data lakehouse with well-sized files, which can improve query performance. You don't want to create too many small files at the end of the day, right? So there is a mode which can perform that, and there's also other mode where you want to just like don't care about the file sizing, you want to go and write it, you can just go and write it as well. So in this case, the file replacement algorithm is going to add the record into the file 3 here. Again, once the files are committed, the snapshot view is going to see the latest version of the Parquet files. And the state as of transaction 2 is going to be reflected in the snapshot queries. Again, incremental query doesn't have to give you the full snapshot. It's going to give you only the new latest view of the records that got affected. Now, the key thing here is, as you can see, for every single transaction, if there are updates and deletes, we have to read the previous version of the Parquet files and perform the merge from the incoming batch dataset and create the brand new version of the files. And this has a fixed overhead, which is going to limit the write latency of your write jobs. But by the way, this is how all other data formats are. Similarly, this is how it's implemented. But with Hoodie, you have another storage type, which tackles this problem where you want to optimize for write latency as low as possible. We'll again describe the similar example here. Let's imagine that there's the same first transaction which have a similar state of the world as in the previous case. So the interesting thing happens in the second commit, is commit 1. Here, instead of, there are again 2 updated records. Instead of reading the previous version of the files, Howdy is going to just append them unmerged into log files. So this is way faster than reading the Parquet file and writing the new version of the Parquet file. So you'll get like as low latency as possible with using the storage type. Now, at the end of the day, somebody has to, like if you want the latest snapshot, someone has to actually give you the latest snapshot, right? So there are like 2 different modes here. The one is the snapshot mode, where on the read side, the Parquet files belonging to the previous commit is read, and the unmerged log records are also read, and on-the-fly merge happens during the read side, and the latest snapshot of the data is being returned. So basically, we are kind of, there is an slight overhead here, which would mean that like you won't get the exact columnar performance you would get with some overhead here, in the case of snapshot query. But with the incremental query, it's same as what you saw in copy on write. But if you want columnar performance, you can actually trade off a slight freshness for columnar performance by using this mode called read optimized view. Essentially what happens here is, in this view, in this case, you are going to read only the columnar files that were committed as part of commit time 0. And what entails is like it basically get the state of the world as of the first transaction. But you'll get columnar performance, which is faster than what you get in the snapshot query. The same way, you have a second transaction where you have updates and inserts. Same thing happens. Howdy is not going to do any merge or anything like that. It's just going to be as fast as possible by appending the data to a log files. And once that happens, the snapshot view again has to perform the merge of the columnar files and the log files and give you the latest snapshot as of commit time 2. No change in the incremental view, and on the case of read optimized view, you are still going to get columnar performance, but you're getting the status of commit time 0. Now, in order to make progress for the read optimized query, to see the effect of the changes that got committed as part of commit time 1 and commit time 2, and also to speed up the snapshot queries, Howdy automatically performs what is called back compaction. This is a completely asynchronous operation. It's not going to block the writes. And the way it works is it basically going to read the base file, which is the Parquet file here, and all the log files, and essentially going to do the merge and create the brand new versions of the Parquet files. And this is again like done with atomically and with no blocking the writer. And once this is done, from the query perspective, from the data being returned, it is the same for the snapshot query. You're getting the same set of data, but instead of reading and doing the merge, it's going to read from the latest version of the Parquet files, which is faster. And again, with read optimized view, you're going to see the effect of new commits that have happened after that. And this architecture allows for low latency ingestion, and very efficient ETL can also be built out of it. Okay, so now just talking about the community, actually like Howdy started in 2016. The initial vision was to basically reimagine data processing through a new incremental processing stack. And Howdy has come a long way right now. It comes pre-installed in 5 major cloud providers' managed data lake solutions. It has a diverse set of PMC and committers group, and it's kind of widely used. Talking more about the community, we have a vibrant and friendly community with 2,000 plus Slack members and 200 plus contributors. The GitHub traffic is quite busy with 10 to 20 PRs per week and thousands of engages. And yeah, PMC and committers group are, of course, growing steadily. To summarize, Apache Hudi is built using RDBMS principles and has all the complete Lakehouse platform features that are free, open source, to be used. And for Robinhood use case, we basically needed a reliable, low latency ingestion and very efficient ETL and analytics processing platform. And Hudi fit the bill for that. So now talking more about the Hudi, and so Hudi offers a complete storage Lakehouse platform features, and Databricks provides an awesome experience, Spark execution experience. But some of these features like Photon and caching are not natively supported with Hudi. And so Hudi supports pluggable metadata syncing. We use it to sync with services like BigQuery, Hive, Glue, and DataHub, and so on. And the community is actually working on creating a bridge between to basically translate Hudi metadata to Delta Lake for native integration with Databricks environment. Okay, so coming back to Robinhood use case. Just to recap on the high-level architecture. So we have a master RDS instance taking writes. Debezium is a Kafka Connect service. It captures changes from the master RDS instance and logs to the Kafka topic using Avro encoded format. The changes are then incrementally read by Hudi Delta Streamer and written to S3 along with the checkpoint offsets. So Hive tables are automatically generated and synced as well. So we do need to create the initial snapshot of the table, and instead of querying the master RDS instance, which our SRE team never advised, so we had to come up with a different solution. So we built a snapshotting service on top of Hudi, which directly reads from read replica and creates the initial snapshot of the table. Okay, just zooming into the CDC path. So the Delta Streamer is a service basically which internally keeps track of the checkpoints from the Kafka consumption. And in Robinhood, we use shared nothing RDS databases. And Debezium is going to read from each of these topics, each of these tables and shards, and they're going to write them into different Kafka topics altogether. And Hudi is going to basically, Delta Streamer is going to automatically union all these changes that are happening in different Kafka topics belonging to the same logical table, and uses schema registry to decode the data and write them to S3. So the Bootstrap path is actually a sequence of 3 different steps. In the first step, the Delta Streamer automatically ensures that it keeps track of what is the current state of the incremental ingestion. It needs to record from where it has to start once it switches to incremental ingestion. So once we record the timestamp, the checkpoints from where we need to consume, we basically wait for the replica to catch up, because the replica is going to use physical replication. And there is some algorithm where we need to check to ensure that the replica is up to date with the master. And once we guarantee that, we are then going to do an initial snapshot of the table and then switch to incremental ingestion from the checkpoints we saved in the first step. So this is going to guarantee that there is no data loss while when we are performing this initial snapshotting mechanism. Okay, so this is basically based on just a slide on our experience running ingestion at scale. So we have around 4,000 plus RDS tables. So at this scale, it's not possible for us to do manage the tables individually, tune them individually. So we did a lot of work on automating many of these onboarding and self-healing mechanisms. We built systems to understand the traffic patterns in the master RDS database and to react to it by either provisioning more resources or less resources depending on how much we need to consume. We also, not all the tables are equal, right? So some of the tables are very critical. And so we need to guarantee some kind of isolation and SLAs for those tables. The way we approached it is we employed a tiering-based approach. So the highest priority tables are have a dedicated Debezium connectors, and they have dedicated resources to guarantee that there is no SLA miss with respect to resource contention. We also, when it comes to this kind of replication, we have to be worried about the data drift, and we need to have a lot of checks like pre-commits, validation checks to ensure that the data is actually same as compared to the source of truth. And again, monitoring and alerting all your friends. So we leverage that to figure out any issues before our customers actually found out those issues. And final slide. And so we started with basically snapshotting from the replica. Because of the bottleneck on the RDS instances, we cannot, some of these ingestion jobs takes multiple hours. And because of the number of tables are there, we are not able to run these jobs intraday. So basically, we have to schedule these jobs once per day. And as you can imagine, the freshness is more than a day. So once we implemented the new end-to-end system, we were able to see that for many of the core tables, we had around 5-minute latency. And all the critical tables are well within the 15-minute SLA that we promised to our consumers. And that's pretty much about. And thank you for open to answer questions.